David J. Dilworth studied cosmology at U.S. Naval Postgraduate School in Monterey, California, by invitation of Emeritus Professor Karl Heinz Kai Wohler, who assisted his professor Werner Heisenberg. David humorously points out how this makes him Heisenberg's grand student. David's superpower is an ability to translate complex and obscure cosmology into plain English. Which is possibly why his award-winning website, cosmologyscience.com, was ranked number one in web searches for best cosmology blog for 10 years. David's goal in publishing his cosmology and philosophy work is to remind us of the minimum criteria for providing a claim which has scientific value, specifically the bright lines between hypothesis and conjecture, and separately distinguishing scientific theory from non-science claim. He's just finishing a paper solving philosophy of science's enigmatic demarcation problem, offering it for publication this year. Dilworth is a prominent figure in the alternative cosmology community and founder of science-based cosmology. His glossary of cosmology principles and cosmology hypothesis application form are useful and popular tools for cosmology students. Due to his extensive and detailed analysis of logical and observational anomalies, he questions many fundamental facets of Big Bang models, noting how primary supports such as universe expansion, cosmic microwave background radiation, and dark matter lack any direct empirical verification, require logical fallacies, or contradict bedrock physics. Dilworth advocates for avoidance of logical fallacies and a return to strictly empirically validated physical principles in cosmology, which leads to static, simmering universe explanation. So, with this, I would like to invite David Dilworth to deliver his lecture.
So, good morning, Kolkata. I see it's nicely cool at your institute, and it's an honor and a delight to speak with you. I'm hoping to inspire you with my enthusiasm for cosmology. This is Kuipu, the largest structure in our universe that we've found so far. It's about 1.3 billion light years long. And here's my talk overview. I'm going to talk about unlimited inspiration tempered by carefully limited hypotheses, not conjectures, and by using calm logic. Secondly, I'm going to talk about logical fallibilism, how my claims about science could be wrong, and so could anyone's. And which finally will end up with which leading models and theories try to explain our universe today. So first, we're going to embrace unlimited inspiration. And this is the deepest view we've ever had from the Hubble telescope. This was a point in space not far from anything known, but the telescope was pointed at a spot that was completely dark, unknown to have anything in it. And Hubble found tens of thousands of galaxies in this dark patch. Now, it did keep its camera shutter open for something like 11 days or a million seconds. But this is what happened, from complete dark to filled with galaxies. And the brand new James Webb telescope has about the same resolution as the Hubble, but it has a different wavelength that it's sensitive to. It can see in the infrared. And so it gets much sharper resolution in some areas because it can see through dust, whereas the Hubble can see only in optical, like our eyes, and it's not quite as capable in some facilities. Once again, and you'll see this, I use it as a place marker between sections. You'll see Kuipu many times during this show. Once again, I wanted you to see the flying through. These are galaxies. They're not stars. 200,000 galaxies, thanks to the European Southern Observatory. This is not an artist's conception. Those are real 3D mapped galaxies. So as recently as 1974, we had only measured about 500 galaxies with redshift. That's not many. And up till the time Hubble was launched, we only had about 1,000 galaxies measured with redshift. It was a painstaking process. It had to be done with a telescope, essentially by hand. Hubble helped us jump from 1,000 galaxies to about 170 billion galaxies. Hubble didn't do it alone. There were loads of other galaxies and instruments available by then. And now the new James Webb telescope has increased the number of galaxies that we've actually measured redshift with to about 2 trillion. So it's been going up in leaps and bumps, but it may be slowing down a little bit. So you heard Wendy Friedman a little earlier in this conference, and she described how cosmology's near future is the golden era, where landmark discoveries are calling. The Sloan Digital Sky Survey puts out they collect about 200 gigabytes of data daily. The brand new Vera Rubin telescope in Chile generates 10 terabytes of data daily. And the European Southern Observatory, also in Chile, has a library of about 1.5 million images and 65 terabytes of data. What this means to beginning students is nobody is ever going to be able to deal with all that data. There's going to be so many treasures hidden in these terabytes and gigabytes and petabytes that you'll be able to come up with just about anything. It's like walking into a gold field and finding gold nuggets everywhere. There's just so much to be explored. And it's there for the taking. Next, I want to talk about logical fallibilism, how science sometimes gets off track. And the idea is that all scientific theories, interpretations, or explanations are not permanent. They're indefinite, provisional, or tentative. Unlike mathematic proofs, like the Pythagorean theorem, math proofs have finality. Once you come up with the Pythagorean theorem, it's never going to be improved. It's done. For the rest of civilization, it's solid. But physical science proofs, when we're observing things and coming up with ideas, they're never final. They're always subject to new evidence or reasoning. Now, that's not entirely true. There's a handful of exceptions, like the number of protons on a certain element. But small things with integers like that and the inverse square law, those are pretty solid. But when it comes to measuring things like redshift distance and the Hubble constant, these, as you will see, have grand differences in accuracy and new evidence coming up all the time. So the Hubble constant I just mentioned, that's how fast galaxies are supposedly receding from us. It's been measured many, many times. There are now 4 different teams as of this year that they've come up with widely differing measurements from 67 to 73. Yet all are strongly confident in their results. Each team swears up and down that theirs is the final answer, which leads us to this bumper sticker: cosmologists are often wrong, but never in doubt. So this is for all the students of India. Does this sound familiar? The beginning of all knowledge comes from humility. Does it ring any bells? It's from the founder of the Institute, Bhaktivedanta. If I hope I'm pronouncing his name properly. This conference is to celebrate 50 years after he created the Institute. So here's my opinion. We need to foster a cosmology culture that's comfortable with uncertainty. My experience is that we need more uncertainty. Well, we have plenty of uncertainty, but we don't often state it when we're talking with the media or the public or between ourselves. So that's my opinion for today. Once again, Kui Poo, I want to keep reminding you of the largest structure in our universe. So this is the third section of my talk. What leading models and theories explain our universe? Well, I'm going to talk about it in two different major categories, size and time. Size relates to a static universe with no expansion, and change in size, which is expansion like Big Bang, or like Paul Steinhardt, who spoke a little earlier, he prefers a cyclical idea where the universe expands and contracts and expands and contracts. The second category is indefinite or infinite versus finite. Big Bang has an absolute finite finish to it and start. It has a finite start, excuse me. So here we are. I hope you can see my cursor here. So we're going to start with the indefinite time, which could be anywhere up to trillions of years. The first static universe descriptions were before history. People have always imagined that our universe was static. Thomas Digges in the 1500s was the first one to put it on paper. More recently, we've had Hilton Ratcliffe from South America. He wrote a book called The Static Universe. And Eric Lerner, who has a book called The Big Bang Never Happened, he talks often about the plasma universe, but he's also a supporter of a static universe. Einstein actually also first preferred a static universe until he was persuaded that his general relativity equation needed an amendment, and he called it the cosmological constant, and it's now part of Big Bang. So then when it comes to expanding or contracting, Big Bang, obviously, there's 20, few people understand this, but Big Bang has about 20 different variations. There's the standard variations like Lemaitre and LCDM, or lambda cold dark matter, which is the most popular one, and the many cycles like Steinhardt describes. But what is not well known is that the steady state idea pushed by Burbage and Fred Hoyle, and the quasi-steady state, also by Burbage, and the plasma universe by Alfvén, those are all expanding or contracting. Those are expanding issues. We have down here on the bottom, I just wanted to pop this in, non-science. The Bible has an idea of how the universe was created, and the multiverse is another one. But both of those don't fall into the category of science as much as some people would like them to be. Big Bang defined. So all the Big Bang models generally propose that all matter, energy, and forces were created instantly from a hot dot, smaller than an electron some 14 billion years ago, and expanded and cooled to what we now observe. Please note how electromagnetism was never involved. Matter of fact, we don't even know, I'll go back here, we don't even know what the supposed force was that caused a Big Bang. But no one has ever asserted that electromagnetism had any part in this. So you're quite familiar with this, I'm sure, that Big Bang theorists claim that 95% of the universe's matter is either undetected, unexplained, or unknown. And the known matter, we've only got about 5%. That's the visible things that you can see, like our sun and planets and asteroids and galaxies and so forth. So here's the general state: expansion models like Big Bang, and then static models. And here's what I think is a pretty dramatic distinction between the two. Unobserved forces. Big Bang, yes, they've got unobserved forces. Unknown matter, right. Dark matter, unknown phenomena. Expansion, inflation, take your pick. Unknown energy, yeah, we've got dark energy. And adjustable parameters. Big Bang has up to usually about 6, but up to 19 adjustable parameters. Sort of like a black box. You can adjust things to make the answers come out how you want. And we got one other one. This was an amusing thing from John's talk just a few minutes ago, where he talked about dark dimensions. That's a lovely new idea. I've also heard of dark magnetism, which I don't know how to incorporate into this, but stay tuned. Another very important thing is that the largest scale force in Big Bang is gravity. They assert that the largest scale matter and forces that influence the dynamics of our largest scale structure is gravity. Whereas in static models, the largest scale force is electromagnetism and not gravity. And we'll go back up. This adjustable parameters static models have no adjustable parameters, no unknown energy, no unknown phenomena, no unknown matter or forces. So Big Bang models need gravity, not electromagnetism, because Big Bang is built upon general relativity's gravity equations. Some people are not familiar with the idea that general relativity is where Big Bang came from, and general relativity is a gravity principle. It's also not widely known that Big Bang expansion models are extremely controversial. So controversial, they've spawned plenty of debate in books, papers, and conferences. Some years ago, this prompted the formation of a growing worldwide group of hundreds of astrophysicists signing a paper called An Open Letter of Concern, and it was published by New Scientist magazine. I think that was in about 2006. And it's not just the people who are questioning Big Bang who are a fringe group. The most prominent cosmologist in the world just won the Physics Nobel Prize in 2019 for cosmology. His work on it is Professor James Peebles. And he said, we have empirical evidence that there is still better theory than LCDM, lambda cold dark matter, to be found. Still a better theory to be found. So supporters of Big Bang include Jim Peebles, Ned Wright, Joel Primack, who just died, I think about a month ago. He was from across the bay from me in Santa Cruz, California. Joel Primack was the guy who essentially was the author of the lambda cold dark matter model. So Big Bang has many basic flavors and 2 optional amendments. Inflation and the accelerating universe. The accelerating universe is the part that got a Nobel Prize on its own a few years ago. And the most popular of all of them is the LCDM. Qui-poo, one more. So I'm bringing you some good news. Dark matter has been found in 2 different ways. And then we're going to talk about how microwave background isn't, expansion's tricky requirements, And the most distant galaxies that we've been able to study have the same ratio of red to blue as nearby galaxies. Red to blue galaxies are old to new. And the large scale structure of our universe is not circular or spherical. So in 1933, a fellow named Zwicky calculated that dark matter must exist when he was looking at the rotation curves of galaxies and clusters of galaxies. He calculated this using the virial theorem, which is a principle that relates the kinetic energy to the average potential energy of a stable system of particles. And he thought something was missing. So he's the one who came up with the idea that dark matter is there and it's missing. It's missing from all of our observations. However, the first group who actually found dark matter didn't find any physical object. What they found was that the galaxy rotation curves are fully explainable without any dark matter. Chuck Gallo, Charles Gallo, and James Feng, they published in 2003, and they published several articles since then. Sadly, Chuck Gallo also passed away not long ago. So here's here's the next search for dark matter, and I would like to say that it's over, and it's actually been found by the Dockham and Conroy team, and it was staring us right in the face all along as ordinary. Admittedly, it was difficult to see, but we can all celebrate and then get back to work. So I'm going to start here with a question. What's the most common star type in our stellar neighborhood? I can't see any hands, but we'll assume you're leaping out of your chair to answer that. So what is our Milky Way galaxy's most common star type? And what type of star is our nearest neighbor? Red dwarfs. Not those red dwarfs. Red dwarf stars, not the Disney dwarfs. Anyway, red dwarfs are the coldest, smallest, and the most common stars. Here you can see in this little picture, there's the upper left is a relative size. That's our sun. And next to it, that medium-sized object, that's a red dwarf star. Three little ones in the center, those are brown dwarf stars, which are smaller and colder yet. And finally, on the right, about the same size as the brown dwarfs, is Jupiter. So that gives you an idea of the temperature and the size the red dwarfs, brown dwarfs are to our sun and Jupiter. So gigantic amounts of missing matter were found hiding as very faint red dwarf stars. You saw because of their temperature, only 3,600 degrees Kelvin compared to our sun, which is almost double that. They're hard to see. In fact, Proxima Centauri is a red dwarf with a mass of about 10 to 12% of our sun's. And in our own neighborhood, our nearest stars, including Proxima Centauri, there are almost as many red dwarf stars as there are all the other types of stars put together. That's kind of a stunning discovery. Once again, here's Quipu. Now we're going to go talk about microwave background. Is it an illusion? What's not widely known is that microwave whole sky resolution is terrible. It's absurdly awful. Our best whole sky microwave data has 58 times worse detail resolution than Hubble. Does everybody know what resolution on a camera is? Well, the whole sky microwave cameras that we use, like Kobe and WMAP and Planck, some of them have better resolutions than the others, but none of them have as good a resolution as a good old camera that you've got on your kitchen table. And resolution is what tells us what the details are, where we can see stars at the center of our Milky Way galaxy, and we can see galaxies literally 11, 12 billion light years away from us. So our best whole sky microwave data is 58 times worse detail than Hubble. Actually, that's wrong. Our best whole sky microwave data is 58,000 times worse resolution. So we're going to talk a little bit more about that in a minute, but we're also going to combine that with explaining how foreground microwaves, it says date, I meant data, foreground microwave data is real, but background microwaves is not real. It's calculated. So the microwave foreground definition is where you have to start, because microwave foreground is subtracted from the whole sky data to come up with background. So foreground microwave radiation is defined as that which comes from known matter sources: stars, planets, dust, gases, galaxies, nebula, anything you can actually see as a physical object that's emitting microwaves. And it's physically verifiable. We can stick cameras up there, microwave cameras up in orbit, and aim it at an area, and we can get readings, literally pictures of microwave areas in our vicinity in almost any direction. We can't get it when we look at the sun. Actually, we can get it when we look at the sun. It's just overpowering. The idea is we can take photographs of foreground microwave radiation. So here is, I'm going to call this a false colored map of microwave radiation, but essentially every image you get, whether it's from Hubble or Webb or any of the microwave satellites, it's all false colored, because microwaves don't have a color. So we have to attribute colors to them to try to pull them apart. Well, here, the red orange in this image is undisputed microwave foreground. All the red, orange, yellow is considered microwave foreground. And the reason is this is a whole sky image, and it's looking, the center of our Milky Way galaxy is that plane right through the middle of the image. And you notice that the microwave radiation is most intense right at the plane of our Milky Way. And it has flares and loops and whirls all over the place. The blue is what's calculated. It's leftover microwave, and we've been calling it background. So microwave background is defined as radiation not from known matter sources: stars, planets, dust, gases, and galaxies. But background is a calculation, not a picture. You cannot take a photograph of cosmic microwave background. We only arrive at it by subtraction. To get the microwave background map, we have to subtract completely arbitrary versions. Okay, they're not completely arbitrary, but they are, every team uses a different version of microwave foreground radiation, and you subtract that from the whole sky microwave map to get the background. Here's the same image as the previous one, but it's in the original colors right from the Planck ESA data set. And this time, instead of the colors are somewhat reversed. So the bluish white in the center, those are the microwaves, also along our galactic plane. And we're going to zoom in down towards in the lower right corner, towards the large Magellanic Cloud and the small Magellanic Cloud. And so you can see pretty clearly how the light blue, whitish areas are foreground microwaves, and how they're pretty distinct, how they always come from distinct sources, like the Large Magellanic Cloud, our nearby galactic neighbor, and the small one. So here's where we're going to look at the terrible resolution of the instruments that have been giving us microwave data for the last 40 years. On the left-hand side, these are the three main satellites that the United States, and the European Space Agency have put up. On the left is COBE, the original one that came up with the first data that essentially killed the steady state universe theory. The WMAP, which Wilkinson Microwave Anisotropy Project, well, that had a much higher resolution. You can see how the resolution goes from very fuzzy on the left one to the middle one. It's fairly improved over the left one, and the Planck is a better resolution yet. But I want to give you an idea here with this picture how awful the resolution is, even with the best ones. So on the leftmost box, each one of these boxes are 10 degrees on a side. The leftmost box has a 7-degree square area outlined on it. And that is the size of COBE's pixel. A single pixel from a COBE image had a 7 degrees by 7 degrees square image. And in the upper right part of that little box is the moon depicted. The moon is only half a degree across. So you can see the comparison of the size of the moon to a single pixel of the COBE data. Sort of dramatic. You can see that when COBE took a picture and it included the moon, there was a whole lot of other space that was emitting microwaves. So also relative to this, everybody thinks, an awful lot of people I speak with talk about how they think microwave resolution is really pretty good. And they think it's about the same as Hubble. Well, at the distance of the moon, the Hubble resolution is about 100 meters. That means it can just make out objects that are 100 meters across. About, let's see, that's about 300, 100 meters is 100 yards, roughly. But the moon's diameter is 3,500 kilometers. So that little red dot up there, that's 3,500 kilometers across. And the Hubble resolution is exquisitely much more detailed. So here's from NASA. COBE had an angular resolution of about 7 degrees across the sky, 14 times larger than the moon's apparent size. Remember, that's for a single pixel of a COBE image. This made COBE sensitive only to broad fluctuations of a large size. Well, that's an understatement, the size of Jupiter. So here's I hope it's an interesting comparison of the microwave satellite's resolution at moon distance. So if you're aiming the 4 satellites, Hubble, COBE, WMAP, and Planck, you're aiming them all at the moon. At that distance, what is the size of something, an object that you could make out? Well, Hubble could see something about 100 meters across. COBE could just make out something that was 25,000 kilometers across, 14 times the moon's diameter. WMAP, considerably better. We're down to 1,500 kilometers. That's actually less than the diameter of the moon for the first time. And Planck, we're talking 580 kilometers, still gigantically more than Hubble's image. So I expect that I've got the idea across right now that Microwave satellites' resolution is absolutely terrible. I realize that is not why they were designed. They weren't designed for high resolution. They were designed to be highly sensitive to extremely faint temperature, the 2.74 degrees of the supposed background. But the problem is when you have such lousy resolution, every single Kobe pixel gathered the light from the whole 7 degrees times 7 degrees, 49 square degree field of view, and averaged all of it to give you a single data point. And that average included the microwave radiation from about 2.5 million galaxies. Every galaxy with hundreds of thousands, maybe millions of stars. Every Planck pixel includes the microwaves from about 50,000 galaxies. So every poor resolution, Planck, WMAP, and Kobe includes the microwave radiation from tens of thousands to millions of galaxies and billions of stars baked in. That foreground radiation, the real foreground radiation, it's unseverable by calculation or any other way. The only way you can pull it apart is with higher resolution. And it's preposterously evidence-free to claim any of those satellites' pixel shows us non-foreground microwave radiation called background. Averaging microwaves means the foreground inherently affects your results. Every cosmic microwave background data point includes microwave radiation from tens of thousands to millions of galaxies. So no cosmic microwave background radiation maps have even one pixel without microwaves from thousands of galaxies. We can't measure places without galaxy clusters to observe background because we don't have any whole sky microwave cameras or sensors with sharp enough resolution that they can see between galaxies. We'd need sub-micro arc second resolution to be able to see those. So microwave background is an illusion. If your angular resolution is poor enough, every foreground microwave pixel is smeared and looks like background, even if every single microwave photon comes from a specific star, dust, or gas. Anything can be a UFO if you're bad enough at identifying things. Anything can be microwave background if you're bad enough at identifying things. So here's my opinion. It's all foreground. When our whole sky microwave satellite cameras get down to sub-arc second resolution, all cosmic microwaves will be identified as coming from matter, stars, dust, and gas, meaning it's all foreground microwaves. No matter how far distant it is, I believe that it's all going to be shown to be identifiable as coming from some discrete matter. Next, we're going to talk about expansion and redshift. I think maybe you all listened to Louis Marmay's presentation on redshift. That he's really a remarkable researcher when it comes to redshift. There's nobody I know of who has got a better grasp of, I think he's identified something like 60 different redshift proposals and evaluated all of them. Anyway, I'm going to I'll defer to him when it comes to redshift, but we're going to talk a little bit more about universe expansion right now. So all of the dozens of Big Bang models are based upon and require some 6 different concepts, including at least 2 conjectures, which mean they don't meet the minimum threshold for science. The first one, it's a real hypothesis, and that is that there's a spectral line redshift to distance correlation. which it is observed. We see that over and over again. And that's how we measure the distance to galaxies and stars. Although its data exhibits a large variance. Now, some people quibble about the large variance, but I would say that the variance with redshift to distance versus the spectral line, I'd say it varies about 10%. Although when you factor in quasars related to galaxies, the number is about 1,000 to 1. It's a gigantic variance. Anyway, that's a real hypothesis, and there is a real correlation between the spectral line redshift and distances. The second one is recession velocity. That's a hypothesis that the redshift distance correlation also means that most galaxies are rushing away from us. So the first one is distance. The second one is speed. And that is something that's never been independently verified. There's no other way to look at recession velocity unless somebody can come up with something clever. Because the recession velocity that is everyone like Wendy and her crew are arguing over, it's incredibly tiny. It's like millimeters per week. So, and it doesn't happen at small scales that we can get out there with a ruler. Anyway, recession velocity is something that we cannot verify. We only take it for granted that the redshift distance means that galaxies are rushing away from us. The third thing is expansion. This is the conjecture that the recession velocity from above requires that our universe is stretching, and that's called universe expansion. That's different than just moving away from us. The fourth one is extrapolation. That's a conjecture that I don't believe is a valid scientific hypothesis, that we can extrapolate backwards, that the purported universe expansion that we may be seeing right now, extrapolate it backwards in time, 14 billion years, to a moment when all the matter and energy were packed together into a volume smaller than an electron. And the fifth one is universe expansion requires not the well-known and studied Doppler effect, but the relativistic Doppler effect. And there's only feeble, questionable experimental results with relativistic Doppler effect. It has been looked at in labs, but I'm not persuaded by the results. And the sixth one is universe expansion does not define or clarify exactly what about space is expanding. Is space a physical space that's expanding, or an abstract space like an XYZ coordinate system? What is expanding? And if it's physically expanding, presumably semi-uniformly, how could we possibly measure that independently of redshift? What independent baseline inertial reference frame could we use? So here's a secret. Well, it's not exactly a secret. If you study cosmology, you'll come across it, but it's not well known, is that universe expansion does not occur on scales smaller than galaxy clusters. There's no expansion on our Milky Way, and there's definitely no expansion within our solar system. And because it doesn't happen at anything smaller than a galaxy cluster scale, there's no way we could ever verify it. So young and old galaxies have the same ratio of old to blue, or red to blue, young to old galaxies. So there's a researcher named Bomi Lee at University of Massachusetts, and they did some study on large galaxies at 11 billion years distance. And they found that large galaxies at that distance, which means they get away from the Malmquist effect, and they found that the old galaxies versus the young galaxies at the great distance had the same ratio as nearby ones. That means there's been no universe evolution. They studied something like 1,600, almost 1,700 galaxies, only 2.5 billion years after the purported Big Bang. And they had the same correlation of morphological properties and star formation properties as we see in the local present day universe. So that means there's no large-scale galaxy evolution that Big Bang and expansion needs and predicts. So apparently our universe doesn't have expansion. Could it be static, not changing in size? The last thing we're going to look at in this is that large-scale structure is neither circular nor spherical. Gravity only makes disks and spheres. Only electromagnetism and plasma makes filaments and sheets. But the universe's largest scale structure is not even close to circular. Gravity making disks and spheres looks pretty familiar. And electromagnetism, lightning and plasma are lightning is plasma. And you notice how electromagnetism makes pretty obvious filaments. Above about a galaxy scale, only electromagnetism and plasma make filament, sheet, and void shapes. And that's a little section of Kui Poo once again, which is why I've been showing it to you the whole time. So Kui Poo, our largest structure, is it round, spherical, circular, or is it filamental, composed of filaments? By the way, these lines, these filaments collecting the large bright areas, these knots of galaxies, almost every data point in there is a galaxy cluster. It's not just a galaxy, but there's billions upon billions of galaxies in all of those filaments. So now we're going to talk about Big Bang and the elaborate nonsense. Big Bang models require undetected matter, forces, energy, and phenomena. Their models are all ambiguous. They lack adequately defined or unstable fundamental terms, sometimes charitably called dynamic or moving goalposts. Employ a minimum of half a dozen, up to as many as 19 adjustable parameters. This is the chart we looked at earlier. Unknown matter, unobserved forces, unknown phenomena, unknown energy. And the largest scale force in Big Bang is gravity. In static universes, it's electromagnetism. So not everyone knows that Big Bang was pulled out of a hat by a Catholic priest named Lemaitre, who dressed it up with some obscure math called general relativity. So the question is, what's the difference between Big Bang and the Bible creation story? And the answer is duration. One of them takes a little bit longer. Yes, there's a bit of tongue-in-cheek with my presentation here. So I truly believe this part, which is, depending on Big Bang, is like using a Paris street map to climb Mount Everest. It's just wrong. You can put, this is from the wonderful governor of Texas, Ann Richards, who said, you can put lipstick on a hog and call it Noreen, but it's still a pig. So I think Big Bang is a hilarious spoof. It's post-posthumous, way beyond the aftermath of anything pre-posthumous. And we should all be asking ourselves, is reality negotiable? Well, Superman might get ticketed for breaking the laws of physics. And here's a picture of a cop writing them up. So static universe models, I promised I'd talk about these. Static universe models have no expansion. By definition, they just stay roughly in one place. They aren't expanding. They may have movement, like I think have you heard from Sandra Faber yet? She's probably going to talk about the great attractor. it, static universe models have no problem with having local galaxies moving towards a great attractor. They just don't have any overall expansion. Static models are just fine with redshift, meaning only a distance correlation, but they reject redshift, meaning galaxies are rushing away from us. Once more, and static models do not require undetected matter, forces, energy, or phenomena. They do not employ any adjustable parameters. It's not well known that Edwin Hubble never believed in the expanding universe conjecture, even though others have plastered his name all over it. Yes, he came up with the principle that redshift means distance, but the galaxies rushing away from us, he never bought into. Andre Assis has written about that extensively. He has a number of remarkable books. So here's a little ballad. For 40,000 fortnights, Ptolemy ruled the skies with his earth-centered universe until its overdue demise. Well, 500 years hereafter, I'm embarrassed to confess, cosmology still embraces mirages for another goofy mess. Gravitational expansion, a self-conflicting view, another Earth-centered blunder, misled by a sexy clue. If space really has expansion, then why not our Milky Way? Bangs galactic contradictions, such tortured disarray. Microwave background with an odor of illusion. Can't be caught by cameras, so blinded by calculations, sell us a delusion. Could it be because big bangers prefer a flashy show, sheepishly using wrong maps, then confess what they don't know? Well, back in our static simmering universe, raise a glass and join our song, sharing hearty cheers all the light year long. Thanks to European Southern Observatory for this wonderful fly through of galaxies. There is no end. And my favorite aphorism, shoot for the moon. Even if you miss, you'll be among stars. Thank you.
Perfect. Thank you so much, David. It was really wonderful, very interesting, very
Oh, can you hear
enthusiastic,
me?
and yes, I can.
Okay.
It was really wonderful to hear the talk. I hope everyone was very interested, and it was very captivating. I always remember now Q-Pu, the largest structure of the
Right.
around. So I'll not forget that. So thank you so much for talking about the universe models, taking us a little bit deeper into the microwave background versus foreground. That was very clear to understand. And talking about resolutions, expansions, and redshift, showing the nice images. Really wonderful. And now I will bring some questions. Okay, the first question is from Kumar Ravi, who is from Swami Vivekananda University, Barrackpur, West Bengal. The question is, which major observational pillars of modern cosmology, such as the CMB, Hubble's law, cosmic acceleration, and phenomena for which dark matter is invoked, which of these are comparable with static cosmological models, and which observation decisively rule them out?
I have yet to come up with anything that rules out a static universe. But the tired light is one thing that um, everybody is on tenterhooks, walking around tenderly.
Mhm.
Dealing with redshift and whether it means uh, anything resembling tired light is going to be the biggest question, I think, to be answered in cosmology in the next few years.
Mhm.
But cosmic microwave background, as I think I've illustrated, I don't believe it exists. And I don't believe expansion exists either. And I think those will be
Mhm.
borne out the more evidence that we get.
Okay, thank you so much.
Does that help?
The next question, yes, definitely. So I will bring the next question to you, which is from Rajesh. He says, can you tell how the dark matter has been observationally inferred? Can we detect CMB using a homemade experimental setup?
Yes, it started with Fritz Zwicky looking at galaxy clusters, and then that quickly was backed up. I think it was Vera Rubin who found that galaxy rotation curves didn't make sense. And I'll try to give you so there's spiral galaxies spin looking like water about to go down a drain. And when you compare them to our solar system, in the solar system, the closer to the sun, the faster the orbit. And the farther out, the longer the orbit. So, for example, Mercury
Mhm.
goes around the sun very, very quickly, and it takes us on Earth, well, an entire year, where I think Mercury's orbit's on the order of 90 days or so, and Saturn and Jupiter, Neptune, and so forth, they take many years to get around the sun. Well, with galaxies that are spiral galaxies that are rotating, it turns out that as you get further and further out, all of them are making one revolution at about the same time. It's almost as though they were connected with spokes so that Jupiter and Neptune and Earth would all be going around the sun in 1 year. And that's called galaxy rotation curves. And I think it was Vera Rubin who discovered that. And those two observations, Zwicky with his virial theorem and Vera Rubin with her galaxy rotation curves, that's how the original hypothesis that dark matter was responsible for the rotation curves and the unusual speeds in galaxy clusters. I think that's the origin of dark matter. Well, we've
Mhm.
been looking for it ever since, and people they've been looking at the very large objects like star size and larger. Well, maybe Betelgeuse type things. And they've also been looking at gas and dust and the very small, from wimps to machos, and every time someone's done an experiment for the past 40 years, they've come up empty. They cannot find any particular object that fits until the recent discovery of all the stars, the red dwarf stars that make up a tremendous proportion of our local galaxy. Now, I don't know if anyone's done substantial calculations on any of that. I haven't done the calculations myself, but
Mhm.
there's something for a grad student or a researcher to take on to see what the fit is. I think it's a close enough fit that it deserves a good look. And
And
there was a
the
second
second,
part to the question. I would say you can't detect it for a couple of reasons. Well, the primary one is you're in your backyard, you're going to be looking up through the atmosphere, and it's all essentially absorbed by the atmosphere. You have to get
Mhm.
outside the atmosphere. even you could from your backyard, you could send up a balloon and maybe get up above enough atmosphere to do something like that. That could be a do-it-yourself project. But maybe a more fruitful way to do it would be to get the data which is sitting. There's Kobe data, there's Wilkinson microwave data, there's Planck data, and analyze the data yourself. Several researchers have done some things like that, and they've come up with some useful answers. So that might be something you could consider.
Yeah. Thank you. Thank you so much for explaining this very clearly. So the next question I'd like to present to you is from Pradeep, Kendriya Vidyalaya Sangathan. The question is, well, the first he says, thank you so much for such an enlightening and thought-provoking lecture. It has truly challenged the way I view the origins of our universe. While I have been reflecting on the traditional Big Bang model and Sir Roger Penrose's conformal cyclic cosmology, I find myself a bit of a crossroads. Given that the cosmic microwave background radiation is used as evidence to support both the singularity of a single beginning and the aeons of a repeating cycle, does the current data actually allow us to favor one over the other? Or have we reached a point where our current explanation leaves the ultimate origin of the cosmos an open mystery?
I'll go with the open mystery.
Sure.
I, yeah, as you probably gathered, I don't believe there is any such thing as microwave background. So
Mm.
anything that depends on that, I'm sorry, is kind of uh, I don't think it has any validity.
Thank you. Um, if I could present your next question. So it's from Roshan. Question is, with the current explosion of observational data, do you think theory is lagging behind data, or are we overfitting models to match observations?
Both theories are I would say they're stuck in the 50s and 60s, and this may be a bit of an overstatement myself, but uh, it seems a little bit like rearranging the deck chairs on the Titanic.
Mhm.
There's so much that is being overturned almost on a daily basis. New data coming from the Webb telescope and from the Vera Rubin telescope and the Sloan Digital Sky Survey. The data is just it's an avalanche. I don't see how anybody, no one person could ever keep track of all the new discoveries, let alone the data. The papers are coming. How many papers were published in the past week on cosmology just related to the Vera Rubin telescope, or well, the Webb telescope? I mean, uh, it's just bewildering how much new data we've got, and the things that are being shown to be get overturned. It's like cosmology needs its own magazine for all the new information that's coming out and new discoveries.
Yes, indeed. Thank you so much. So maybe I'll just take one last question, keeping the time in mind. So the last question is from Yogesh from Indian Institute of Technology, Bhubaneswar. He says, as observations have expanded from billions to potentially trillions of galaxies, how has this improved our understanding of large scale structures like voids and bubbles? Have these structures become more clearly defined or more complex than we initially expected?
I think you've nailed it. It's become more complex. I think the biggest leap forward in understanding happened with the Valerie de la Parent, Margaret Geller, and John Hookra project for the Center of Astrophysics. In 1989, they mapped a couple of slices of our nearby universe in 3 dimensions. It was the first time we'd ever had really good 3 dimensional data. And Margaret, on her own, I think maybe with Smithsonian Institute, put together a video, which I have buried somewhere, but I don't think it's available anymore. But if anybody can find the video called So Many Galaxies, So Little Time, it's what inspired me to get into cosmology. It it's like the little video I showed you from the ESO about flying through galaxies. It's very much like that. And it was such a stunning change where we could only vaguely speculate on what the 3D universe looked like. And all of a sudden, that team of three found 3 dimensional structures. They found filaments, they found sheets and walls, and strikingly, they found the voids, large areas with no galaxies in them. It was just, to this day, it's still jaw dropping to me. And yes, we've learned more since then. We've found things like Quipu and many other sheets and walls and filaments. But I think that original research that showed the 3 dimensional vision of our universe, I think that's still the most spectacular advance, maybe in my opinion, since the beginning of modern cosmology. My hat is really off to those three. That was marvelous.
Yeah.
So, is it getting more complex? Yes, but I'd say we're only really adding to it. What the wonderful three with Valerie de la Parent, a French researcher, John Hookra, who has passed away, and Margaret, who just retired. What they came up with, I think, is the most significant thing in cosmology. And they came up with essentially the stuff that's been added to since then, but I don't know if if the new evidence of large scale structure has really changed that much from the 1989, 1991 data.
Mhm. Thank you so much, David, and it was really wonderful. I mean, as also hear from the questions, everyone was very interested, excited, and just thought provoking, forcing us to think a little bit differently. Thank you so much
Great.
for taking your time out, sharing this with us, and QPU, the largest structure. Thank you so much.
You're very
Um,
welcome.